Good, then let's start. We have been talking about the emergence of line tension in reaction diffusion systems, in particular in mass-conserving reaction diffusion systems. I showed you this. This is a simulation of such a system, and when you run it, you have an interface that forms, and the dynamics is such that the interface length is minimized. And then we said there are laws that we know from thermodynamics, namely the Gibbs-Thomson relation that describes such a phenomenon, namely surface tension that minimizes the interface length between different density liquid domains. And I showed you the calculation. The calculation relates the surface tension, the curvature, the jump in the density delta rho, and the resulting gradients in the chemical potential. And as you know, any gradient in a chemical potential drives mass flux. This mass flux is such that it shifts mass from the hump to the valley, and thereby it is evening out the interface, thereby minimizing its length. And you should note the arguments that I used in my lecture was just a thermodynamic argument. I did not use any kind of mechanics per se. I was just basing everything on minimizing free energy functionals. Now what we have been up to is this. We have been looking at mass-conserving reaction diffusion systems, and for simplicity, I wanted to focus on a multi-component, multi-species system where each species just has two components that we call membrane and cytosolic component. You can phrase the equation in terms of the mass and cytosolic density as you see it here, or you change variables. And as you change variables, you can go into a field space where you have the total density being one of the independent variables and the other one being the mass redistribution potential, the eta potential. And then when you rewrite the corresponding equations in terms of those two fields, what you do get are the blue equations on the right-hand side. And those blue equations are a continuity equation for the density, where the driving force are gradients in the eta potential. The eta potential itself is not a thermodynamic potential, but is given in terms of its own equation of motion that you see as the second equation, right? So, but still we do have this idea of the eta potential being analogous to a chemical potential by driving mass flux. So what we study in both cases are interfaces, and we consider these interfaces as really having a very, very small interface width, such that we can go to the limit where the interface width L int times the curvature along the backbone, also along the interface, is much less than 1. Curvature is defined here as a local property at a particular point along the curve that we say is parameterized in terms of arc length. And then you have on that curve a unit tangent vector and a corresponding unit normal vector. And what we wanted is to link the properties of the interface with thermodynamic quantities. For liquid mixtures, we just had it on the slide. We found that the jump of all the densities across the interface, so let's say from a high value to some low value along the interface, this density jump times the corresponding shift in the chemical potential is given by a surface tension times the curvature on the system. Okay, so the central object is that we do have a surface tension that is the material parameter linking the curvature on the right-hand side. So this object with the chemical potential shift. Okay, and by that you have a process which minimizes the interface length, and the process that does that is the mass transport driven by chemical gradients. We also want to study this for multi-species mass-conserving reaction diffusion systems. There we also have these interfaces and the equations you see here. So the central object that we have and that we want to analyze is what is the shift in the eta potential that's induced by the curvature, and what is the line tension, if there is any, right? But what is the line tension? And can we, based on looking at the shift in delta eta, derive an analogous Gibbs-Thomson relation that we have here? So is there a generalization of the Gibbs-Thomson relation to a system which is out of thermal equilibrium because we are describing something that's driven by chemical reaction and not driven by relaxation to a thermodynamic minimum? So that's the agenda, and I have written profile equations, but for now let me go and have a little recap of differential geometry of curves. Some of you may know this already, but some not. So this is really very elementary differential geometry of curves, and we only need here curves that are embedded in a flat space, so just two-dimensional curves. So we have the curves that I just drew. You have a tangent vector and you have a corresponding normal vector, and we can define these quantities if I'm denoting the curve as R of S, and S being the arc length, then the tangent vector is defined as the derivative of my curve vector with respect to arc length, and I'm defining arc length by normalizing my tangent vector to be a unit vector. Right, then we can have the normal vector, which is also a unit vector, n, which is perpendicular to t, and we want n also to have unit length. And then we can use the combination of the normal and the tangent vector to define the curvature. And the way this is done is simply by watching the normal to walk along the curve. And as the normal walks along the curve, it will tilt by a certain amount. And this tilting of the normal vector, that's how the line here curves. So it defines the curvature. And there's a sign convention to be made. So I'm saying that the derivative of the normal vector along the backbone, the curve, is proportional to t, that's for sure, because they are normal to each other. And now the sign convention is that I'm taking this to define the curvature with a plus sign here. So if it turns to the right, then we take the curvature to be positive, and if it turns to the left, we take it to be negative. And with that, you then infer that if you were to write the derivative of the tangent with respect to the arc length, then you do get minus the curvature kappa. So here we have kappa positive, and that's a region where you have kappa being negative. Okay, then you can define a basis. And what we ultimately want to do, we would like to look at what happens close to the interface. So that means we have to study a coordinate system that's proper as a coordinate system in the vicinity of my interface. And therefore, I'm choosing an interface coordinate system which follows locally the curve. So I use a curve linear coordinate system. And for that curvy linear coordinate system, there are many choices, of course. The one I'm taking here is one where I take one of the unit vectors that makes the basis of my curvilinear coordinate system to be the tangent vector plus x times ds times n. So what I'm doing here is that I'm using a system, so I should have written this before. So my system x of s and x is the vector that points to the curve, so the one that we already have. And this is now capital X, so don't confuse this with this here. So I'm looking at a point here that moves along the curve. And then I'm moving up here along the normal and define by how much I move up along the normal the distance in the normal direction. And that distance in the normal direction, this distance I call x. So here along the normal, I'm defining this as the normal direction. So I define the position in this coordinate system to be plus this distance in the normal direction times the normal vector at s. Okay? So that's what I take as the position in the vicinity of the system. And then the unit vector that goes in direction of s is the derivative of this object here with respect to S. That's the same as ds capital X of S and X. Okay. That's one of the unit vectors. The other one is just the one in the normal direction. So E that I call Ex, that is the derivative of this vector pointing into my curved linear coordinate system with respect to x. Well, and that's then simply given by n. So that's my coordinate system, and you can rewrite the AES in a more explicit form. So ES, as you have it here, is the tangent vector plus the normal distance times the S of n, but the S of n, as you can read here from above, is just the curvature that you have times t. That means this here is 1 plus the curvature times t. So it still has the same direction as the tangent vector, but it's rescaled. So this is now multiplied by 1 plus kappa of s. All right, and then we have it. Then we have the local reference system. And once you have that, you can define a metric. So with that, we have a metric, meaning a metric tensor that we can define, which is just a scalar product of all of my unit vectors. So one of those is the scalar product of the, not the unit vectors, the base vectors. So the scalar product of my basis vectors, and they're not normalized here. So this is 1 plus kappa times x squared. Oh, sorry, I forgot something here. Right, I should have complained because there is this x here as well. Then I do have the components of the metric tensor in the normal direction. Well, that's just n squared, so that's 1. And all the other ones I don't write down because they are all identical to 0. Okay, so that's what we have. That's defining our metric tensor, and we can also get from that the determinant. So G is the determinant of our metric tensor, and that's then simply 1 plus kappa x squared. Okay. So that defines just the very basic features of a curve in two-dimensional space. And recall, if you want to know what the Laplacian is in that reference frame, and that's something I don't really show you, but just give you the results. So the Laplacian for that is such that if you act on a function f, then the Laplacian can be written in terms of the metric that we just calculated. So it's 1 over the square root of the determinant of the metric. Then you have d di, square root of g, g ij, dj acting on f. Okay. That's what you have. That's the Laplace-Beltrami operator for the Laplacian, and the corresponding quantities that you need to know in order to infer that Laplacian is the following. So you have, well, in our case, what we do get is just what I already have on the board, right? So it's already there. The GI J's are not those ones because they are actually the inverse of that. As I shift the indices from lower indices to upper indices, I get the inverse matrix, and that's what appears here. That's the inverse matrix. And all right, that's what you have. And to leading order, and that's all we need in the analysis of our system, you can insert the relations that we have here. And then to leading order, what you get is that this is ds squared f plus dx squared f plus kappa of s dx f. Okay. And here I'm neglecting all terms which are higher order in kappa than this linear term here. Okay. And that is a term that's new, and this I want to call a term that corresponds to a geometric drift that you have because you have a curved interface. Okay? And as said, this is just algebra to get to this step here. So now that you have that Laplacian, we can simply use this relation in the following analysis as our differential operator acting in the vicinity of the curve. So now let me recall what we had. We looked at a flat and a curved interface, and there we considered the profiles of the corresponding density profile. And for that, we had the following equations. We had 0 equals 2 dm alpha dx squared rho 0 alpha of x plus f alpha tilde rho naught vector of x eta vector. Okay, so we have a set of values for the eta potential that are fixed, that don't depend on space, and you have the profile vectors rho of x that determine then the profiles for each of the components in a flat interface region. If you have to have a curved interface, then the whole thing changes not by much. All we have is now, because we look at a particular point along the interface, particular arc length position S, we just have the geometric drift term and the derivatives in normal direction of the interface. Now times the interface profile for a finite curvature kappa at that point in normal direction, plus the reaction term evaluated for the profile vector with finite curvature as a function of x, and the eta vector also for a finite curvature. We do have two equations here. One equation is the equation for a flat interface, and the other one is the question for a curved interface. And to be clear, we are now doing two things. one after the other. So our task 1 that we have in analyzing this set of equations is that the profiles for a flat interface are stable to small perturbations. And these small perturbations are in rho, and they are in eta. What I actually would want is that these are really stable, not just to small perturbations, but also the big ones. But mathematically, I'm only able to do linear stability analysis, so that's the only thing I have really access to.
Why do you want to do this?
Because we want to expand around such a stable solution and want to know how it evolves then further. If we were to find that this profile is actually not stable, then we don't have an interface. Right? So we really have to make sure that our interface that we talk about exists and is stable. Otherwise, we have no starting point for asking the question, what would happen to the interface as I deform it and create some curvature? Okay? So that's what you need to first show. That's our first task. And the second task, task 2, that we have in analyzing this problem is, once we know the flat interface is stable, what happens with a curved interface, and how is the curvature of the interface changing the eta potentials and the profiles? Okay? So based on a stable solution for a flat interface, what are the changes in eta and rho due to curvature of the interface? Okay. That's the second question, and the second will then lead us to the Gibbs-Thomson relation that generalizes the one that we have for liquid mixtures. All right, so let's go back now to this task 1 that we do, which is for a flat interface. And then the deviations we look at, the delta rho and the delta eta, are with respect to the flat interface, but they don't have anything to do with asking what happens as you change the curvature. I'm just meaning now I'm changing eta up and down along the interface, and I'm changing the profile of the interface. So let's plot that. We have here our normal coordinate. We have the interface profile going from low to a high value. Then this is rho for one component, and I have also the value of eta for one or all the other components. We want to know, what if I were to change eta up and down, or what if I were to change the profile also here, right, on the plateau, up and down? Is this relaxing back to some steady state for the flat interface? That's our task 1. So let me start from the very beginning. Let's just start from the plateau stability. So here I'm asking, really, what is the feature of this and that plateau to the right and to the left of our interface, are they stable? For that, I just look at the corresponding equations for the well-mixed system. So I neglect all gradients because the plateaus are flat by definition. And that means delta rho is 0, and delta eta is minus the reaction terms that we have for the eta potential. That's just a well-mixed dynamics that one has. So for that, we do have a set of nullines, eta star of rho. Those are the ones where the reaction terms vanish. They are the equilibria that we have. So they are defined by all the f for all the alphas as a function of the density vector gives values eta star of rho such that this is identical to 0. This generalizes the concept of a nullcline to a nullcline surface, because now we have a vector-valued reaction term as a function of vectors of densities. So that's our nullcline surface, and this defines all the reactive equilibria that you have. The plateaus, right, they should be those reactive equilibria, because if they are not, they would be, the system would not relax to those away from the interfaces. And we need to make sure that these plateau values, rho p and eta star of rho p, they need to be stable. So this needs to be a stable fixed point in our system, otherwise the plateaus wouldn't really exist. So for that, you need a criterion of stability. And this criterion of stability you can infer by looking at the equation of motion and consider spatial perturbations of it. And for that, you can then show that the matrix that we have, okay, this one here, this is the generalized matrix from the nullcline criterion. So remember, for one single species, we had df tilde d eta as the condition for having a unstable fixed point, by this being negative. This was our criterion, the nullcline slope criterion for instability. And now, for a multi-component system, we just need a criterion for a vector-valued reaction. So for a nullcline surface instead of a line for the reactive equilibria. So the system, the plateaus are stable in that case if the eigenvalues of that matrix have all positive real parts. In case there would be a negative real part, you would get an instability, and that's just the generalized slope criterion for a multi-component system. And I leave this up to you to show, because it is really a straightforward generalization of our calculation that we had for a one-species system. Now coming back to the problem of the interface. So let's look at the interface stability. Still looking at the case of a flat interface. So as said, we want, after having established or choosing parameters such that these plateau values are stable, it could still happen that even if we choose those plateau values to be stable, that our interface is not stable. And we need to make sure that we pick a proper regime such that this is the case in order for us to have a good starting point for doing an analysis of the properties of those interfaces. So for that, we expand in delta rho alpha of x and delta eta alpha. So for that, for the flat interface, we get an equation of motion expanding for a flat interface with these deviations with minus delta alpha beta dm alpha dx squared delta rho beta of x minus a Taylor coefficient of this evaluated at the unperturbed interface times delta rho beta of x and the corresponding Taylor coefficient with respect to eta beta, also evaluated at the unperturbed interface delta eta beta. And this object here that we have defines our linear operator acting on delta rho beta of x. Yeah.
So the fact that this delta eta is independent of space is a simplification, or is there a reason for this?
This is not a simplification because the very feature of an eta potential is that it's constant at stationarity. Right? dt rho equals Laplacian of eta, dt rho being 0 means that the Laplacian of eta is 0. And that means with no flux boundary conditions that we always assume that the eta potential is flat at stationarity.
But if we're considering now a perturbation, kind of perturbation itself be space dependent?
Well, to leading order, not.
So in a way, the changes in space overall are like more important than.
Yeah. So you could always add other perturbations as you like, but they would relax quickly to 0, and we want those perturbations that are the most dominant at the interface.
Should this delta at least depend on the curvature of the point?
The curvature comes later. Right? So for now, this is all flat. Eta will change. The constant value of eta will change as a function of curvature. That we will see next time, not this time. So now we're just looking at the flat interface, and we want to know, is that stable? All right, so this is our equation that we have. And we have then an eigenvalue problem to solve. And for that, we define a scalar product, which is the natural one that we have here because we look at interfaces and we want the scalar product to measure how much the two vectors u and v, how much they have a scalar product that deviates from 0. That's our scalar product that we have. And the interval that we choose is such that our b is much larger than the interface width. Otherwise, we would not really cover the whole interface region. So for that scalar product, the corresponding operator, that it's the adjoint operator with respect to that scalar product, is concerning the diffusion part just the very same as the original operator. So that doesn't change. But because we have a scalar product, if we have a matrix there, then the adjoint operator has to be the matrix with the interchanged indices. And that's minus d rho alpha f twiddle beta evaluated at 0. And you see, because you cannot guarantee that this d rho alpha f beta is the same as d rho beta f alpha, that we have a non-symmetric part here, and therefore, in general, this is not the same as L alpha beta. So our operator L that we have here is a non-Hermitian operator. Okay, and then what we want is the major contribution to the interface shift. And there's one contribution which is the Goldstone mode, which is not what I drew. It's not this wiggly thing that you could also have in the same way as you could have wiggly things in eta. The dominant contribution here is the one where you simply shift the profile by a certain amount delta from right to left or left to right, physically speaking. Okay, formally, this doesn't really matter because we can really just use the equation in a formal way and do the analysis. So now let me do it in the formal way. If we take the equation for the flat profile, so the equation star that you have right here, so this equation, and if you take that equation and take a derivative of that equation with respect to delta x, right, you will then have an equation where you multiply this equation from the left with operator delta x. And let's do that. So from that, you get 0 equals the sum over beta minus dm alpha delta alpha beta dx squared. And then for that term, I'm just getting dx rho beta 0 of x, just by adding another derivative. But that term here, I'll take a chain rule. I have to do this. This is delta rho beta f twiddle alpha evaluated at the unperturbed interface. Okay? And that means, right, that this operator here acting on delta x rho beta is 0. So this is really the same as L acting on dx rho beta 0 of x being 0. So you formally get this, that this operator that we introduced acting on the gradient of the stationary profile for the flat interface is 0. But behind that, physically, is just the fact that a translation of your profile, so rho of x going to rho of x plus delta, is not changing the physics in any way. It's just a shifted profile, and that is rho of x plus delta dx of rho of x. Okay? And that should not change the physics. So this object here must be a null mode under the dynamics which you see here. Okay? This dx rho is our Goldstone mode that we have in the system. And that's something we are certainly not interested in when we want to look at the stability of this interface. All we actually want to know is how is the interface then stable against shifts in the eta potential. So we would like to project out this part that corresponds just to the shift of our profile. So now given that, we have L dx rho, we call it rho 0 because that's our 0 profile, right? This is, still here. So given that this is 0, you can infer if this linear operator has a property which is called that it's closed. You know that the corresponding adjoint operator has a null mode. So F is the null or 0 mode of L hat, which is corresponding to the mode dx rho alpha rho 0. Okay? And that we use now. The fact that we do have such a V naught, we don't calculate it. We just say there is something like that. And using that, we project onto the equation. So we say we take this 0 mode of the adjoint operator, and we project onto the equation motion that you see here on the right-hand side. So project onto the expanded equation of motion that we have on the right-hand side. So what we do is we project on the linear operator acting on delta rho. This is this, right? This part of the equation. And then we have to add here minus sum over beta d eta beta f tilde alpha evaluated at the unperturbed profile delta eta beta. This is then 0, right? That's what we have. But now, right, because L acting on delta rho is the same as L dagger acting on V, because it's the adjoint operator, that's how it's defined, we can use that L dagger on V is 0. So this part here is actually 0, since V is a 0 mode of L dagger. Oh, sorry, I shouldn't write 0 here because there's a dt eta here. So I'm just looking at the right-hand side now. This is this. And this then has to be equal to the left-hand side. So this is V times dt delta eta. Okay, so that's my equation of motion. And you see, we have now really made it much simpler. What we got rid of is the dependence of the eigenvalue problem on a profile that's an explicit function of the normal direction. That's gone now. And all we are left with is an eigenvalue problem that contains the constant shifts of the eta potentials in the interface region. So we do have a closed eigenvalue problem for the shifts in eta in the interface region. Okay, so what do we get from that? Let's look at this. So let's start now from here. This is a scalar product. So we have a sum over alpha. We have the time derivative. We have delta eta alpha. And then we have, from the scalar product, an integral from minus b to b dx v alpha of x. Okay, so that's what we have from this. And this is equal to the right-hand side. So this is then minus the sum. The scalar product gives a sum over alpha. Then we have a sum over beta here. We again have the integral over the interface from minus b to b. Then we have d eta beta f alpha, all evaluated at the unperturbed interface, v alpha of the normal coordinate x times delta eta beta from the shift of the chemical, of the mass redistribution potentials. Okay, what's this object? Well, this is just the total change across the interface, and let me give it a name. I just call this delta V alpha, okay, by definition. Okay, so this is true here for any alpha, and therefore I can write this as an equation of motion for a given alpha, so a given component, delta eta alpha. This is then equal to minus the sum over beta. Then I have here d eta beta f alpha twiddle evaluated for a given null mode in component alpha. So let me define what I mean by that here. This average here is an integral of minus b to b dx, the object that you have here, times v alpha divided by what I just defined as delta v alpha. So it's just a shorthand what I have here for the lengthy expression that I have here on the line before that. So it's dividing by this and then using a shorthand notation for that integral over the surface domain, delta eta beta. So that's the equation that we have. Okay, and now I have a second condition for stability, and with that we then close for today. So my first condition, where is it? Was for the plateaus to be stable, so have a stable anchoring of my interface at a high and low density regime. I do need that this null-Klein criterion for the null-Klein surface is fulfilled. Otherwise, the plateaus wouldn't exist. And here, I need a similar argument or similar condition. So when is that stable? When do the delta etas relax to 0? Well, if this here is really negative, and that what you see here on the right-hand side is a positive object. So the condition for that is now that this object here has only positive eigenvalues. Okay. So the eigenvalues of this one have to have positive real parts. Right? And that concludes for today just the very existence of a stable interface profile by these two necessary conditions. Right? This is necessary for the plateaus to exist, and this here is necessary for the interface to exist. These are not sufficient conditions, as we heard from your question, right? What if I have a perturbation in delta eta that's spatially varying? What if I have very strong perturbations? Is this still stable? We don't know from that calculation, but we sure need to have as necessary conditions that this matrix has only positive real part eigenvalues, and that our derivatives with respect to eta also have just positive real parts. All right, and next time we look now at the curved interface. So we now know we have a stable flat interface, and then we can ask what happens if we now curve the interface, and what are the implications of curvature on the change in profiles and on the change in the eta potentials along the backbone as you change the curvature. All right. So I hope this was clear now. Questions?
Regarding the ghost stone bones, it's here like this complex rho is indeed 0 eigenmodes, but it's not trivial for me how one can see it as a ghost normal, because when we really look at the profile of rho of x, this slope, partial rho, partial x, I cannot compute to the shifting of profile.
But this is simply this.
Yes, but I mean, if looking at this, then rho of x plus delta should have different value.
So with this being a solution, or with this being a solution, this has to be a solution, the same.
Okay.
So that has to be 0. That's the argument.
Solution by means of acting the
Of acting on it with the linear operator. Right? And this is something which is not what we're asking, because that's a trivial thing, that you shift the profile and you can shift it and nothing really happens. It's a marginal mode. Right? There's nothing shifting back or pushing it forward. There's no backward or forward velocity moving the interface. That's something we don't really want to ask about. And formally, as you do the mathematical analysis, you can project it out and just focus on the changes in eta. Yeah?
Yeah. So here we are saying that if you want stability, this matrix has to be positive.
Yeah.
But at the same time, we are not saying anything about the growth of delta rho, right?
Delta rho is given by this other equation, which is left out because it's trivial. It's nabla squared eta. And if I'm only looking at eta is constant, I don't need to worry about this.
Okay.
Right? So if you now ask this other question you have been asking, what if eta is actually varying in space? It could. Then you need to look at both equations and check whether that's stable as well. And that I did not look at because I wanted necessary conditions for the stability.
So in that case, where delta eta is constant, we are guaranteed that both delta eta and delta rho
dt rho, the time derivative, so is not changing.
Yes.
Yeah. So you would have dt rho is 0. So it's marginal, neither negative or positive, it doesn't change for a given constant eta. Yeah. Therefore, I don't need to look at this if I consider constant eta. Okay. All right, so that's it. And next time we'll ask the question, what happens if the interface is curved, and how does that lead to changes in profile and eta potential? Good. Thank you.